In a previous video, we talked about how even though the integral test can be used to show that a series converges, it cannot be used to show what it converges to. So what the sum of the series is, it doesn't work, and I showed you why. Whenever you're using the integral test, the idea is that you have this continuous decreasing positive function that you're using somehow, let's say, those sort of lower rectangles to be the actual sum of your series. And because of the way that these work, the green terms are the sum of your series, the green rectangles. The blue graph is the integral of your function. So this is the blue and this is the green. There is this sort of error here in the middle, right? And so you cannot say that these two are equal. The integral does not equal the series. And in fact, I'll just put this here to really emphasize this equation becomes correct only if I say that they're not necessarily equal. But they may happen to be equal at points, but they only happen to be equal if the blue graph is perfectly horizontal, or if for some reason there's some oscillation, but in that case we're not even going to be using the integral test because we need the function to be decreasing. So there's always some error in between this, and that does not tell us the sum of the series. It tells us that the series converges, but it doesn't tell us what the sum of the series is because of those red errors there. So if we want to actually find the sum of the series, how would we do it? We would do it this way. We are going to define this new sequence, which I call a sequence of remainders. This is nomenclature that I've invented. So maybe somebody else in a different class is not going to be using this notation. They will use this Rn if needed, if they want to estimate, but they're not going to call it that necessarily. I like to give certain things names when I think I want to refer to them multiple times. So to begin with, this is going to be the sequence of remainders. And what's that sequence, right? If you remember the sequence of partial sums, those are the SNs that you see right here. So S1, again, is going to be A1. S2 is going to be A1 plus A2. S3, A1 plus A2 plus A3, and so on. And Sn being all terms up to An. So these are your Sn's. And S, capital S, is the actual sum of the series. So n equals 1 to infinity of an. So S is going to be adding all of them without stopping. Okay? Sn stops at n. S3 stops at 3. S2 stops at 2. And S, without any index, doesn't stop. We just add forever. So when we subtract these two, what we get is the remainder of this series. So when I do S minus Sn, I have on S all terms, and on Sn all terms up to n. So S minus Sn will be all terms after S, after An, right? So it would be An plus 1 plus An plus 2, right? For example, what will be, if I go back a little bit, what will be R1? R1 will be S minus S1. So that means I take away A1 from all terms. So I add everything from A2 onwards forever. R2, excuse me, will be S minus S2. So it will be A3 because I took A1 and A2 away, plus A4 and so on. R3 is going to be A4 plus A5 and so on. And so R is the remainders. So whatever Sn is lacking for you to get the whole sum of the series. That's why it's called the sequence. I call it the sequence of remainders, though it is called remainder, even if it's not called the sequence of remainders most of the time. So you can also call it the tail of the series. This is also the tail of the series. The tail of the series. right, after n terms. And this is exactly what this is saying. So you're adding all terms starting from n plus 1 all the way to infinity. That's what Rn is. Okay? And one thing that you can note is that as n grows, so it's basically the same series, but I'm starting earlier and later, excuse me, on n. If I'm really far away, the red arrow that I have here is a lot smaller. So this is not also the same as the integral, but it's closer to the integral than the whole thing, than the whole series. So as I go forward, Rn gets closer and closer to the integral starting at n. So basically what we're saying is that Rn is very, very close to the integral from n to infinity. That's what I'm saying. So how can I possibly estimate the actual sum? Instead of just trying to say that the integral is what it is, I just add a bunch of terms, make n very large, and then integrate everything after that to estimate how much is missing, because for large n, those are close. So I'm going to solve an example to explain this idea to you. Here's the theorem that summarizes this idea. So I'm closing this, I'm opening these intervals. So before we're able to apply this remainder estimate theorem, you have to make sure that you have a positive function, that your function is continuous, and that your function is decreasing, just like the integral test. So it has to be a function to which the integral test is applicable. And it needs, a series to which the integral test is applicable. And also your series needs to converge, because if it doesn't converge, you don't have to estimate the sum. If it diverges, the sum is infinity, right? For a positive function, for a positive series. So how can you use it? Let's do this example. So approximate the sum of the series, this one, using the first 5 terms. So by that I mean, okay, item A, I want to add everything from 1 to infinity, but I can't. So I'm going to add only from 1 to 5, which is why they said 5 terms. It's that 5 here. So I'm just going to do 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared. So I'm going to add all of these. 1 plus 1/2 plus 1 over 9 plus 1 over 16 plus 1 over 25. And then I'll add these as a fraction. Are those hard to add? I can make this 100, no problem, but this 9 is not nice. I could make it a 900, but will that be better for me? So the 2 and the 16 are not a problem. There are 2 3s here and 2 5s. So I think I got to do 25 times 9 times 16. And that's going to be 3,600. That's what I think. There's no 5. I think that's right. So this guy got to multiply by 3,600. And this one's going to be half, of course. The 1/2. And then fix my 3,600 here. And then the 9, I have to, let me do 3,600 divided by 9. That would be 400. Right. And now 1 over 16, let me do 3,600 divided by 16, and that will be 225. Yeah, I think I had to go 3,600. And then 3,600 divided by 25, and that will be 144. So that is going to be, just add all of these using my calculator here. You can use yours too, just double check my math, it helps. So I get 6169 all over 3600, which should be approximately 1.71, and let's say 4. Why not? Okay. So this is what I get from adding just 5 terms. Okay. And you can see that the last term here is super small, 1 over 25. 1 over 25. 1 over 25 is 4 over 100. So it will be 0.04. So the next terms get smaller and smaller. But is this a good approximation? How far from the actual sum here do I have? Do I have my estimate? Actually, this is incorrect. This needs to be an approximation. But how far do I have it? What is the error in my approximation? How can I estimate it? I use the error estimation here. I use this. So we're going to solve an integral, and my Rn, which is the remainder, is going to be between these two integrals. So I do the integral from n to infinity, n here being 5. So I'm going to integrate the function 1 over x squared from 5 to infinity. I do 5 to infinity, 1 over x squared dx. And so what will that be? It will be, I have x to the negative 2 from 5 to infinity dx, which will be add 1 to the power, divide by the new power, 5 to infinity. So that will be minus 1 over x, right? But then I plug in infinity, and plugging in infinity means taking a limit, minus, I plug in 5. So this is going to be a 0, and this is going to be a 1 over 5, which means that this is a 0.2. So this is the possible error, the maximum error in my approximation from the theorem I just showed you on the screen. R5 is less than or equal to the integral 5 to infinity f of x dx, which is 0.2. And because my series is decreasing, I don't have to worry about subtracting 0.2. Excuse me, it's 0.2. Subtracting 0.2 from this value. I just got to add, because I've added 5 terms to get the actual sum. I'll just keep adding more. But I know that whatever other terms I need to add, they don't add up to more than 0.2. So that means the error is 0.2. So this means that my sum, 1 to infinity of 1 over n squared, is less than this number that I've calculated, 1.714 plus 0.2. So it could be at most, approximation here, 1.914. 1.714 plus 0.2 is 1.914. So at most, this is what it is. But also, this is the maximum error that I have. But also, there's a minimum error that I could have. So the other side of the theorem, if you go back, says that the error, the remainder, is more than this integral. So basically, I have n plus 1. So in my case, since I'm adding 5 terms, I'll do integral from 6 to infinity. So I do the same integral. I've already solved the example, by the way. I've estimated the error, but I want to make it more and more specific. And so if I add an integral from 6 to infinity now, then I know my error is more than this. So 1.74 is definitely not the right answer. I know the answer is more than that, but it's that plus something, and that something is between what I'm calculating now and 0.2. So this is going to be same integral as before, right? So I'll have x minus 1 from infinity to 6 like this. So I'll do applying infinity gives me nothing. And then this is 1 over 6, the value of this integral. So I know that Rn is more than 1 over 6, which is 1.67, more or less. So that means my error, though it's not more than 0.2, it is for sure more than 1.67. So that means this is got to be more than 1.714 plus. I did this wrong again. I'm getting tired. This is 0.167, like this. So 0.167. Okay, so this is the minimum value that the sum could have in my estimate, and this is the, over top there, is the maximum it could have over here. And this is the most it could be, and this is the least it could be. So even though I don't know for sure what the answer is, I have a pretty good estimate. Let me add these numbers so we can work with it. It's 1.714 plus 1.167. 0.167. So that is 1. This gives me this. The actual sum from 1 to infinity, 1 over n squared, is between 1.881 and that number, 1.914. So you see, we got a pretty good estimate for this number for the sum of the series, even though we only added 5 terms. Of course, you need a calculator for that, but most of the time, I'm okay with you using fractions for your answers where you don't have a calculator, so that's also okay. See, it's pretty small error, pretty small range. Now, let's go all the way up so you can see item B. The question is, how many terms would I have to add to ensure that the error is under 0.0005? Let me take this all the way down with me so that we can solve B. So now we're not given how many terms. For A, we were told that we were adding 5 terms. We're told this for A, but for B, we're not. We want to know how many terms. So the question is asking what's n. And we want to get our n to be less than 0.0005, which means we need the integral from n to infinity of f of x dx to be less than 0.0005. Okay? Because we know Rn is less than this. If for sure the integral is less than 0.0005, then so is Rn. So I can solve this inequality. I solve this integral, set it to be less than this. So I'm going to solve the left-hand side first. As you know, this is going to be minus 1 over x from n to infinity, like this. So it needs to be less than this. How many? 3 zeros it was, right? Yes, 3 zeros after the decimal point. When you plug in infinity or basically take a limit, this is 0. This is minus 1 over n then. So you need 1 over n to be less than this number. And how can you make 1 over n be less than this number? You can take n multiply over, take this number multiply, divide over on that side. So that will then mean that we're doing, gotta calculate this. This is not bad, okay? I know many of you won't like this, but you don't need a calculator for this. Some of you are gonna see that you don't need it. Some are not gonna like it, but you don't need a calculator to find this number. You can multiply first. I like to do that, to multiply by, that would be 10,000 because I want to move the decimal place away. So I need 4 zeros to do that. So that's 10,000 divided by 5, less than n, right? And then maybe I can double the fraction top and bottom to get 20,000 over 10, like this. And then dividing by 10 is fine. So I get 2,000. So what does that mean? We need to add 2,000 terms to ensure that we are within 0.0005 of the actual sum of the series.